So we're going to go over the third quiz. General results did not go well. So hopefully this will help clarify some issues. So we got this structure here. It's a frame for supporting a roof. That roof has some snow on it. Snow has a distributed load. So what I'm going to do here, what do we want to do? First things first, let's draw a free body diagram of this structure. So okay, so we got external force 25 kilonewtons. This 15 kilonewtons per meter distributed up top over that 4 meter span. That the resultant of that would be a 60 kilonewton force downwards, acting at the center, obviously. We've got a X component support at G. Got a Y component support at G, and we're going to have an H reaction that's only in the Y direction. It's only in the Y direction because those are rollers. We're really past the point where people are mistaking stuff like what supports do. So yeah, if you have a pinned connection on rollers, it's only got a vertical component to your reaction. If you have a pinned connection that isn't on rollers, it only has force components. There's going to be no moment components there. The pinned connections allow rotation. That's their defining trait. At first glance, perhaps at first glance, you might have thought that there wouldn't have been any zero force members, but now that we kind of drew our free body diagram here, we'll look at what's going on at H. We'll just do a quick free body diagram of the joint at H. Got HY, and we're going to have EH, and then we're going to have DH, and those are the only forces. EH and HY are parallel to one another, so, and there's nothing else there that can provide it. DH is the only force there that would have any X component, therefore it needs to be zero. So that's a zero force member. So we're just going to cross that out. Likewise, magnitude of EH is equal to HY. So let's solve for our reactions. First off, while we got a chance. Easiest one to do. If we do the sum of the forces in the X direction, that'll be GX minus 25 kilonewtons is equal to 0. Therefore, GX is equal to 25 kilonewtons. That way. And if we want to do figure out what HY is, we can just do a sum of the moments at point G, and it's going to be equal to 0. So taking that HY times that 6 meter span, so this is a 6 meter span here, minus the 60 kilonewtons times the 3 meter span, so that's 3 meters right there, 60 kilonewtons times 3 meters plus the 25 kilonewtons times that 3 meter span there. Now again, always keep in mind we're going about this point, so the 25 kilonewton one is causing counterclockwise rotation, as is HY, and then the 60 kilonewton one is causing clockwise rotation. So we're looking at positive on the HY one, positive on the 25 kilonewton one, and negative on the 60 kilonewton one. So all that is equal to 0. So solving for HY, and move the solving for HY, that's just going to be 60 kilonewtons times 3 meters minus the 25 kilonewtons times 3 meters divided by 6. So HY is going to be 17.5 kilonewtons. And then to solve for GY, sum of the forces in the Y is equal to 0. That'll be GY plus 17.5 kilonewtons minus 60 kilonewtons is equal to 0. So solving for that for GY, GY is going to be equal to 42.5 kilonewtons. So we've solved for what our reactions are. We also know that the magnitude of the force in our EH is the same as HY. Having said, if we want this thing to balance, obviously when we do our sum of the forces in the Y direction is equal to 0. That's equal to 17.5 kilonewtons plus EH. So EH needs to be 17.5 kilonewtons negative 17.5 kilonewtons. So that's compressive. Let's have a look at embers. I put embers down. There should be members. Members with identical internal loads. To look at this, let's look at a quick free body diagram, ABC. So ABC, it is a bar or a hoist or a joist or something that has multiple forces acting upon it, including at its midspan and along the length. So some people put that was our 0 force member, whereas it's not even a 2 force member. It's it's going to have internal loads and axial and in bending as well. So it is definitely not a 0 force member. And it's going to have these two. Oh wait, sorry. Default assumption is we're working with tension, so I'll put that there. So yeah, it's got those forces. So let's see, it's AD. This is DB. This is BE. And this is CE. Then we got those forces up top. So if we take a if we look at this thing and we just take a moment about this point in the center here, everything on the top symmetrical, DB and BE don't show up in the equation, and AD and CE are also symmetrical. So essentially, the only way, like, you know, if we got a pin here, and we're pulling on this, and we're pulling on this, and then let's replace the what's going on up top with the resultant, and we're pushing down here. Then, you know, taking a moment about that pin, the only way for this thing to not rotate is if these two forces are the same, as long as they're the same distance out from the pin, which they are in this case. So AD needs to be equal to CE. As well, so that's, you know, you would have gotten points if you had gotten to that full marks. But as well as a bonus, if we here, I'll just go back up to this one. If we go up to this one here, you know, if we have a look at this and we say that some of the forces in the x direction need to be equal to 0 for the stuff that's acting on that is acting on the bar ABC, then, well, so the vertical load, that doesn't matter at all. We've got AD and CE, and they're at the same angles, just in opposite directions. Like, you know, this angle here and this angle here, that's the same. So, and their magnitude's the same. So we know that whatever AD is pulling or pushing on the bar, CE will pull or push on the bar an equal and opposite amount. So therefore, the same thing has to be going on here. Whatever force dB is pushing or pulling on the bar with in the x direction, then B also has to be pushing or pulling on the said bar in the opposite direction. So dB and BE need to be equal to one another too. So I'll just dB is equal to BE, AC, wait, no, AD is equal to CE. So we don't know what those are yet, but we can start getting there. So we've got, I'm gonna write down a few knowns here. So again, this is negative 17.5 kilonewtons internal there. I'll just jot down the lengths of these members. So the length of GE, it's going to be the square root of 6 squared plus 3 squared. So that'll be root 45 meters. BE and DB, square root of 3 squared plus 3 squared. So it's going to be root 18 meters. CE, square root of 3 meters squared plus 1 meter squared. So that's going to be root 10 meters. So we can, let's have a look at what's going on with G. So at joint G, we've got this we got the reaction force, 25 kilonewtons. We've got the other component of the reaction force, that's what was that, 87.5 kilonewtons, I think. I'll just double check that. 82.5. I turn that 2 into 7. We've also got GE. Wait, no, that's GC. That's GC. And we've got this one here, that's GE. So, looking at this, we know that we can solve for GE because it and the 25 kilonewtons are the only ones that have any x component to it. So, sum of the forces in the x is equal to 0. 25 kilonewtons plus GE times its unit vector in the x direction, which is going to be 6 meters divided by root 45 meters is equal to 0. So solving for GE, we get negative 25 kilonewtons divided by 6 times root 45. That gives us GE is equal to negative 27.95 kilonewtons. So from there, we can solve for what our GC is. So our our sum of the forces in the y direction, that's equal to 0. So we got 42.5 kilonewtons plus GC. And then since GE is compressive, that'll be minus. So it's compressive, so it'll actually be pushing down here. Yeah, actually, I'm just gonna. Here, I'll redraw that here. 27.95 kilonewtons. There we go. So minus the 27.95 kilonewtons times its a unit vector in the y direction, which is going to be 3 meters divided by root 45 meters. So we can solve, and all that's equal to 0. So we can solve for our GC, 27.95 times 3 divided by root 45 minus 42.5 gives us GC is equal to negative 30.000. Hey, I'm going to say exactly negative 30 kilonewtons. There's one of them that we need. There's another one that we need. So let's I'll just negative 27.95 negative 30 in kilonewtons. So next up, well, we can start solving for these forces. So I figured that the easiest one to do here would be starting with D here, joint D, and then find what AD and DB are. So we've got a compressive force coming from below, so that'll be a 30 kilonewtons. We've got the load of the 25 kilonewtons. And then we're going to have AD, and we're going to have DB. That's a bit too steep. It's a 45-degree angle. DB. Okay, so we have two unknowns here, And we've got two equations we can use to solve for it. All right, sum of the forces in x and the sum of the forces in the y. So that's solvable. So we'll start with the sum of the forces in the x. That'll be negative 25 kilonewtons plus AD times its unit vector in the x direction. So that'll be 1 meter divided by root 10 meters plus dB times the unit vector in its x direction. So that'll be 3 meters divided by root 18 meters. All that's equal to 0. Then I'm not going to simplify that yet. We've got I'm going to have a look at the sum of the forces in the y direction. That's equal to 0. So that'll be 30 kilonewtons plus AD times its unit vector in the y direction. So 3 meters divided by root 10 meters plus dB times its unit vector in the x direction. 3 meters divided by root 18 meters is equal to 0. So we can, so again, two equations, two unknowns. So again, we got this dB times 3 meters over 18 meters, times 3 meters over root 18 meters term on each in each equation. So we can just say move that over to the other side, and then now suddenly we've got two equations that we can equate directly. So our negative 25 kilonewtons plus AD times 1 over root 10 is equal to this, which is also equal to this. So 30 kilonewtons plus AD times root 3 meters over root 10 meters. So from there, it's not too bad to solve for what AD is. So if we subtract AD times 1 over root 10 from each side, move that over to here. This term becomes a 2 over root 10. And then subtract 30 kilonewtons from each side. We're left with negative 55 kilonewtons is equal to AD times 2 over root 10. And so negative 55 divided by 2 times root 10. That gives us an AD that is equal to negative 86.96 kilonewtons. And you'll recall that that is also, that also needs to be what our CE is on the other side. So, yeah, we're left with that. And then now that we know our AD, we can solve for what our dB is relatively simply. So we've got two equations up here we could use. So let's see if I can just copy this equation right here. copy that. I'm going to paste that. And I'm just going to plug negative 86.96 kilonewtons into the spot where AD was. And then we can solve for what dB is. It was a terrible looking, it's supposed to be a plus sign. So negative 3 over root 18 dB is going to be equal to 30 kilonewtons minus 86.96 kilonewtons times 3 divided by root 10. Negative 52.498 kilonewtons. So that, no, dB, not dP. So solving for dB, the negative 52.497 divided by negative 3 times root 18. That gives us 74.24 kilonewtons. That's dB. You'll also recall that that also needs to be equal to BE. So I'm just gonna, so 74.25. So that's here, that's there. Negative 80, what was it? 86.96. That's here, and then that's here. And then ABC, that's not a two-force member. So, it doesn't have a single internal strength, internal load that is acting upon it throughout. It's got a combination of different got a combination of bending moments and internal and normal loads that vary along its length. So again, two-force members are two-force members because they don't have any forces acting upon them at the midspan at all. Well, that's not the case for ABC. So yeah, that is how you go about doing that. And then summary shape. As per usual for filling out a quiz, just sketch a little summary table and we'd be good to go. Cheers.